Hello. Um, okay, you should be able to see the desktop.
Yep.
Okay, and not many people here today. I'm not sure why. Half the class is missing. Okay, let's see if they join in later. Okay, what we're going to do is, well, first, let me stop and say, has anybody got any questions about the homework assignment? Any question about what we've done last week or about the homework assignment? Any questions about this stuff? Anything?
I might have some questions tomorrow for
Okay,
office hours.
okay, sure. Yeah, so if you have questions, if questions come up, just send me an email or come to office hours. Okay, so then what I'm going to do is, okay, let me download language 0. I'm going to start talking about language 1 also. Okay, clean up a little bit. Okay, so language 0 was a language just of trees. Okay, language 0 is a way to describe tree data structures. Okay, and it's not clear what that has to do with programming languages. Yeah, so right now we're going to try to make a transition from this idea of describing tree data structures to describing at least a baby programming language. Okay, and the baby programming language we're going to start with is just arithmetic expressions, a language that describes being able to add, subtract, multiply, and divide numbers, which is, it's a subset of every programming language. So it's a good place to start. Okay, now remember, language 0 is very abstract. It just says that a tree is a root and one or more trees. Okay, that's all it says, and it lets us express these things in a language, so we can say that A, B, C is a tree. That's a tree with root A and a left branch A and a right branch, a left branch B and a right branch C, and A, B, C, D is a tree with root A and 3 branches, and A, B is just a tree with a root and 1 branch, and A is a tree by itself. So all 3 of these are trees of height 1, A with 2 children, A with 3 children, A with 1 children, and this one's a tree of height 0. That's just A by itself. Okay, so and I can make things more elaborate by, like, if I make this, there's a subtree. Okay, so A is the root. It's got a left child B, then it's got a center tree, which is a root C with a branch E, and then a third child D. Okay, so we can describe trees. Okay, and then our code we have a program that takes these strings and parses them into a tree. It builds a tree. If you remember this class, I couldn't decide what's the best name for it, build tree or parse tree. It technically, what it's doing is it's parsing the tree language and building a tree. So the name of the class is Parse Tree, and it has this one static method that called build tree. Okay, so it's doing 2 things at once. It's actually doing 2 things. It's parsing these strings in the tree language, and it's using as it parses them, it builds a tree data structure. So it parses these strings and builds a tree data structure. Okay, and one way to use this is the way we remember. Here's a tree, And here's how you build a tree in Java, which is messy. Okay, it's a real mess to build these trees. Okay, so what would be nice is to, instead of having to write all this code to build a tree, it'd be nice just to write the tree. Like this tree is easy to write in its tree language. Well, see, I didn't write it here. In the tree language, that tree would be A with a branch B with branches E and F. Then A's next branch is a C. Then A's next branch is a D. And D has one tree G in it. And G has a tree H with child K. Then G has a child I. Then G has a child J. That ends G, but that ends D, and that ends A. Okay, there's the language for that tree. Okay, so this tree is represented by this string in the tree language. It'd be nice to be able to use that string to build the tree data structure. Okay, and that's what the next example, remember, that's what we did in the next example. This one, example 2, it says, take that string and call build tree on it. So pass that string to build tree, and build tree will build us a tree data structure. So instead of having to build the tree the hard way, we can kind of build the tree an easy way by having this parser parse the string and build the tree for us. Okay, and then there was a whole bunch of examples. Like in the next one, example 3 just said, here's a bunch of strings in the tree language. Each one we could write a for loop that loops on them. Take each string, build a tree, and then we could do things with the tree. We could print the tree out in we could print the tree out in what's called the pretty print format. Yeah, this is the tree language for the tree. See, that's the tree language for the tree, but it's a little bit hard to read these. Like, you know, if I just told you to go back here and read this, it's a little bit hard to read. So there were other ways to format it. If you run this program, that guy could be formatted this way. Then you can say, oh, it's A with a left child of B and a right child of C. B has children E and F. C has a child D, a child G. D has child G. G has child H. H has child K. But G also has H, I, and J. So, you know, a column here are children. Okay, so the children of G are H, I, and J. The child of H is K. The children of B, or the children of A are B and C. Okay, the children of B are E and F. The children of C is just C. If this column, there's only D, so C only has one child, D. Okay, that's called pretty printing. Taking this thing and printing it out this way is called pretty printing. Okay, and your homework assignment is to write other pretty printers. You know, there's different ways you can pretty print that tree. Okay, so once you have the tree built, you can do different things to the tree. Okay, now what's that got to do with programming languages? Okay, that's just a quick review of language 0. Language 0 becomes a basis for everything we're going to do, pretty much almost everything we're going to do later on this semester. So we're going to turn now to language 1 and see the connection between this tree language and real programming languages. Okay, so actually, let me stop a minute and just do an example. I think I've mentioned this before. Okay, here's a real basic thing. If I tell you 1 plus 2, that's an arithmetic expression. Okay, but I can think of that as a tree. That's the sum of 1, and 2. Okay, now here's a more interesting example. If I take 2 plus 3 times 4, okay, you know that really means, because of order of operations, that really means you have to do the 3 times 4 first. Okay, now here's a way to say that in a tree. I'm taking the sum of two things. I'm taking the sum of the number 2 with the product of three and 4. Okay. Okay. So this tree structure represents what I'm doing. I'm taking a sum. See, that's the last thing I do. I take the sum of two things. And what I'm really thinking of is this is grouped as 2 plus the grouping 3 times 4. Okay. So I'm really, I don't need to put the grouping there because the order of operations tell me do the multiplication first, but that's the same thing as this. So this is a subtree. That's the times 3, 4 of a bigger tree. That's the sum of the 2 in this subtree. Okay. Here's another example. If I write 2 plus 3 times 4, notice that that's the same numbers, same operators, but now I'm grouping it a slightly different way. Now I'm saying do this first. Now this is the subtree. So that's a tree that would look like this. The product of two things. It's the product of the sum of two things, the 2 and the 3, that gets added to the product with 4. Okay, so this tree represents that expression. This is the subtree of that product tree. Okay, so operators represent the root of a tree, and the operands are the branches of the tree. Okay, so the operator is the root of a tree, the operands are the branches of a tree. Okay, and this turns out to be a really useful way to think of arithmetic. Okay, this tree, thinking of an arithmetic expression as a tree, turns out to be one of the magical ideas in programming languages. Okay, let me give you another example. Suppose I write if x equal y, then print x, else print y. Okay, in a way, that's a tree. There's an if tree, and an if tree has 3 branches. I don't remember if we did this before, but think of an if tree as having 3 branches: the Boolean part, the then part, and the else part. Give myself some room, spread the branches out a little bit. Okay, so if thing, an if is a 3-way branching tree. Now this one is a equal operator. That's a subtree. See, this becomes a subtree. It's an equal operator with 2 operands, an x operand and a y operand. And this is the then part. The middle branch is the then part. That's a tree that has a print function as its root, and that print function has one branch, which is x, and this other last branch is another print function with a branch that's the y operand. Okay, so statements in programming languages can be thought of as trees. These are called the abstract syntax trees. Okay, so this thing's called the abstract syntax tree. This is sometimes called the expression tree, which is another word for it's a special case of an abstract syntax tree. Expression trees are abstract syntax trees for arithmetic expressions. So this thing is the expression tree, which is an example of an abstract syntax tree. Okay, and here, this piece down here is an expression tree. This is the expression x equals y. Okay, but the if statement, we don't call the if statement an expression tree. We think of, for the if statement, we think of it as having an abstract syntax tree. Okay, now all these can be turned back into, now once we've taken this and turned it into a tree, we can turn that tree back into our tree language. So then this would be the plus of 2 with the product of 3 and 4. And this would be the times of the plus of 2 and 3 with 4. Okay. And this one would be, if I turn it back into, if I take the tree and turn it back into the tree language, it's an if statement of the equal operator with x and y. And it's the print root with branch x and the print with branch y. Okay. If you've seen other languages, this might look familiar. This is what Haskell looks like, or what Scheme or Lisp look like. Same with this. There are actually programming languages that use this notation rather than this notation. We call this the infix notation. We call this the prefix notation. Infix notation, prefix notation. I mean, this is just your regular programming language, but this is its prefix notation. Okay. What we're going to do is we're going to use this as our programming language. What we're really interested in is, we're really interested in this stuff here for now. This is going to be our programming language. And it turns out that if I want to evaluate a program, this tree data structure is what's so helpful. What we're going to see is that when you take this expression and you make it a tree, now you actually have a way to run the program. What's a long time ago, people realized that these trees, like this is a baby step towards getting towards a compiler. Okay, compilers let you run programs, but compilers are actually kind of difficult. This is a step. This is the interpreter's step towards running a program. If you give me this and you ask me to evaluate it, or if you give me this and you ask me to evaluate it, turns out that the best way to do that is to build this tree out of it. If you give me this and ask me to evaluate it, or if you give me this and ask me to evaluate it, what I really want to do is build this tree. Because a tree is a data structure that my program can process and I can make sense. There's a really kind of nice way to make sense of the idea of evaluating this tree. So for example, if you go back up here, if you evaluate this tree, what it is it's a post-order traversal of the tree. To evaluate this tree, I evaluate its left branch. Well, that's a 2. Then I evaluate its right branch. Well, to evaluate its right branch, I have to evaluate this guy. To evaluate this guy, I evaluate his left branch. That's a 3. I evaluate his right branch. That's a 4. Now I know what his left and right branches are. They're 3 and 4. Take their product. That's 12. Okay, now I know what this guy is. He's a 12. I know what this guy is. He's a 2. So then I can say, oh, now I can do the plus. It's 2 plus 12 is 14. So that's a post-order traversal. I evaluate the left, I evaluate the right recursively, then I do this operation. Like down here, I want to evaluate this. So I have to evaluate the left. Well, to evaluate this one recursively, I have to evaluate his left. Well, 2 is 2. Then I have to evaluate his right. 3 is 3. 2 plus 3 is 5. So 5, now I know the left side of this guy is a 5. The right side of that guy is a 4. So now I can take 4 times 5 is 20. A post-order traversal, evaluate the left, evaluate the right, do the operation. Evaluate the left, evaluate the right, then do the operation. It's called post-order traversal because you do the operation after evaluating the left and evaluating the right. And it's real easy to write this in code. That's a lot easier than trying to figure out how to evaluate this thing. See, this is just like, this is a string. And notice you read it from left to right, but you don't evaluate it from left to right. Yeah, and this one you read from left to right, but you don't evaluate. Well, actually, sorry, this one you read from left to right, but you evaluate it from, well, let's see, you're going to end up doing this guy first, then you're going to be doing this guy second. Your hand down here, you're going to do this one first, then you're going to do this one second. If you try to process this string, it's really hard. There are algorithms for processing strings in infix notation. They're very messy algorithms. There's something called the train track, the train track algorithm, or the two-stack algorithm. They're really kind of messy algorithms because sometimes when you read this from left to right, you would say, oh, I do this one first, then I do this one. But sometimes you do this one first, then you do this one. Okay, like in this one, it was do this one first, then do that operation. Here it was do that operation first, then do that operation. But notice that here, there's only one rule. Post-order traversal of a tree. Once I've got this guy written as a tree, I only need one rule now. If I can convert this thing to a tree, there's only one rule, post-order traversal. How do you evaluate that guy? Evaluate the left recursively, evaluate the right recursively, then do the operation. Okay, and the tree holds the order of operations in its structure. What is messy order of operations here turns into the structure of the tree here. That's the brilliant idea, that the messy order of operations here turns into the structure of the tree here. Turning this into a tree is going to be hard work. We'll see eventually how to do that. But what's interesting is that once you have the tree, processing it is easy. That's why we're going to start, our language is going to be this tree language. Building the tree from the tree language is easy. Building the tree from this is simple. Building the tree from this is trickier. Building the tree from this is simple because that's the tree language. Building the tree from this is kind of hard. We'll do that later. Building the tree from this is pretty hard, but building the tree from this is easy. And now we have a way of doing this if statement. Now, if statement is kind of it's kind of a post-order traversal, but it's a little bit messy here. Post-order traversal here was, evaluate the left branch, evaluate the right branch, and do the operation. An if one, the way you do it is, you evaluate the left branch. If it's true, you evaluate the middle branch. If the left branch is false, you evaluate the right branch. So notice you don't traverse this whole tree. See, our more general ideas, when we take a piece of language and we turn it into a tree, we don't traverse the entire abstract syntax tree. Sometimes we skip over pieces. So the way you traverse an if operation is you go to the left branch and traverse it, evaluate it. This thing will evaluate to a Boolean. If it's true, then you traverse the middle branch and you ignore the right branch. If this guy's false, then you ignore the middle branch and you traverse the right branch. Okay. Eventually, later on, we'll see things like, what if I have a while loop? Okay, here's a little while loop. Okay, I'm going to turn that into a tree. Okay, it's a while thing. A while tree has two branches. It's got a Boolean branch and a body to it. Okay, the Boolean branch in this case, the Boolean branch is a greater than operator with two children, two operands. It's the greater than of x with 0. Okay. Now, over here, what I have is it's essentially, it's like you can think of it as a semicolon operator. You know, I'll write it as a semicolon operator with two branches. The first operation in the before the semicolon and the second operation after the semicolon. In fact, I'll drop that semicolon because there's nothing after it. So I'm using like a JavaScript type notation. So I've got this like semicolon operator, and the semicolon operator has a left branch and a right branch. If I had a third statement here, then the semicolon operator would have three branches to it. Okay, so I have two statements. Okay. Okay. Now, what's the left branch? The left branch is see if I can have enough room to type this. The left branch is a print of X, and the right branch is an assignment operator. It's an assignment operator with an X on the left-hand side, and on the right-hand side of the assignment operator is on the right-hand side of the assignment operator is a subtraction operator with two operands, with the subtraction operator has an X on its left and a 1 on its right. Okay, so there's an abstract syntax tree for that piece of code. Okay, if I turn that abstract syntax tree into my tree language, I get something like this: while greater than x0. Okay, and then I'll just write I'll just write the semicolon operator of print of X and a assignment of X to the subtraction of X and 1. Okay. Okay. Now, if I can turn this into this, it's not hard to see how to evaluate it. The way you would evaluate it is you would say, okay, a while loop goes to the left and evaluates that. Okay, that's the recursion. The evaluation of a while loop goes to the left and evaluates this recursively. Well, the greater than of x and 0 will return either true or false. If this thing returns true, you go and do the right branch. But if this thing returns false, you're done. Okay, so the while's got two branches. You evaluate the left branch. If it's true, you evaluate the right branch. Then you go back and evaluate the left branch again. If it's true, you evaluate the right branch. If it's false, you quit. Yeah. So if this is true, you evaluate the right branch and go back and evaluate the left branch again. When the left branch evaluates the false, then you're done. Then this thing would evaluate to saying, well, do the left branch, do the right branch. That's That's a sequence of two statements. This thing would evaluate by evaluating this guy, then printing it. This would evaluate this guy by going to the right-hand side, evaluating this operation, and then putting that value into that variable. Okay, so eventually we'll see how to turn all of, we'll write an interpreter that walks this tree and does all those things. Okay, so everything you write in a programming language has an abstract syntax tree way of representing it. If statements, while statements, function calls. What's going to get a little bit tricky is when we start talking about what's the abstract syntax tree for function definitions and function calls. That's when things start getting complicated. When we get to functions, things get a little bit harder. Okay, but it's not so hard to imagine what an if statement would look like as a tree, what a while statement would look like as a tree, and what arithmetic looks like as a tree. Okay, so the tree language, now the tree, what's really tying all this all together are trees. Everything is a tree, but every tree can be written in the tree language. And then we're going to take a shortcut. We're going to make the tree language our programming language. That's what the Lisp people did 50 years ago. They said, this is kind of hard to work with, so why don't we just program in the tree language? Why don't we just write things like that? Yeah. Why not just write our language as a tree language? So they invented the Lisp programming language, which is essentially a tree language. I mean, if you go and Google Lisp examples, I don't know if we can get a couple quick examples. See how, beginning of a tree, there's this, there's the thing that's the root of a tree, left branch, kind of a right branch. You can see that, they're using parentheses and items inside nested parentheses, like there's, and the language is essentially, it's not exactly 100% our tree language, but it's very, very close to it. Okay. See, here's an if statement. There's 1, 2, 3 branches. See, that's how you read this. There's 3 branches of an if statement. And this statement has a conditional branch, the then part, and the else part. Okay? So there's an if statement written in branches. Okay, so the if statement in Lisp is exactly written the way we talked about it here. This is an if statement in Lisp. Okay, and they when this was invented, it really was kind of them saying that this notation here is too hard to work with. So let's work with this easier notation here, because this can be turned into a tree real easily, because this is a tree language. This takes a lot more work to turn into a tree. This takes a lot more work to turn into a tree. But if you write it this way, that's a tree language. So it's trivial to turn into a tree. They knew that what they wanted were trees. They wanted an easy way to describe trees, so they wrote their language as a tree language. Eventually, they came up with better parsing algorithms. And also, they came up with more powerful computers. Back in the 1950s, when Lisp was invented, writing a parser on the computers they had was kind of hard. So the program that translates this into a tree was just too slow and took up too much memory. So they did a shortcut. They said, we would like to program like this, but our computers aren't quite fast enough, so we'll program like this. But then people got used to this notation. They actually liked it, and they started sticking with it. So Lisp begot Scheme, which begot Closure. So you have all these languages now that use this tree-like notation as the basis of the language. So very modern language like Closure is still using this notation. Let's see if there's a nice example of it. Something that really obviously looks like a tree. Well, there's the print. See, look what they're printing. Oh, there's a perfect example. Like this piece here is a tree with a print loop. It's got one operand, which is a plus of 1 and 2. So there's a tree. Okay, and here's another tree that's a print of. Now this tells you, this declares something to be a string, but you can see that the language is written in, like, here's a line that's just a tree. There's the root, and it's got a left branch. Well, actually, it's just got one branch. So it's a root. It's a require statement, and the require statement's written as a tree. The keyword requires the root of the tree, and this is the one parameter to it. Okay, so that's a tree with a root and one node below it. Okay, and if you go through, you'll see that pretty much the language is a language of trees. Okay, modern computers have no trouble parsing this. We'll learn how to parse this later on in the semester. So we'll go back to this notation. The reason for using this notation now is because some people just like it. Some people think it's got, there's many people out there who think that it's a nice notation to use. From our point of view, it's a quick way to get at writing an interpreter, because parsing this stuff is actually kind of hard. And you could spend the whole semester just talking about parsing. Like parsing C++ and Java is very hard. The languages are complicated enough that it's beyond the scope of a class like this. Like we could not write a parser for C++. It takes man years to write a complete parser for the C++ language or the Java language. They're pretty hard to parse. Now, a parser for a subset of C++ is not that hard, but still not very easy. A parser that can parse something like this is still going to be a couple hundred lines of code, whereas parsing this is 10 lines of code. It's just this build tree. Parsing this, we've already written it. It's where is it? This, well, this is our parser right here. The thing that gets a tree, this thing that gets a tree is our parser. And it actually looks like a lot of code because it does a lot of error checking. Remember, we went through it a little bit the other day. It actually is much longer than it needs to be. Well, it's as long as it needs to be because it's doing a lot of checking to make sure that there isn't an ill-formed statement. So it's both parsing and syntax checking at the same time. If I was willing to assume that my strings never had syntax errors, I could shorten that parser by a lot. But then if you gave it a string that had syntax error, it would just crash. Okay, so instead of saying that you have to give me perfect, it's actually kind of educational. I probably should show it to you what it looks like with no error checking, because then you can see the pure logic of the parser. Okay, but it's actually pretty simple. If you strip out all the error checking in here, it's a very simple little parser, because it's parsing this simple tree language. Okay, so it's parsing, it just parses this guy here. A mistake is if you like when you misbalance the parentheses. Well, somebody's got to be able to, you have to worry about somebody giving you strings with unbalanced parentheses. So the actual code has to worry about that kind of stuff. But that's the truism in all programming. Error checking is usually the vast majority of your logic. When you write real code, you end up spending more time error checking than you spend writing real code. So that's what you see here. There's probably more logic in here that's error checking than there is logic actually building the tree. Okay, so it's actually, I think maybe I'll do it. I'll strip out all the error checking from this, or you can try doing it yourself. Like strip this down to what would be the pure parser without any error checking. The thing that would work on correct strings and crash on incorrect strings, which is that, there's nothing wrong with that. It's kind of nice to write that just to see the logic. Something that works when you give it a correct string, and you don't care what it does if you give it an incorrect string. Okay, all right. So we have our tree language. It's really a shortcut for not having to parse complicated things like this. We want to avoid, for now, parsing what looks like real programming languages. So we're going to use this tree language, because the tree languages gives us what we really want, the abstract syntax trees. We're really interested in the abstract syntax tree. That's the first step of every real compiler. Every compiler starts off by taking your code and building an abstract syntax tree of it. That's the first step of a compiler. Okay, and so that's what we're shortcutting by saying, well, our language will just be the language of trees. Okay, so we'll program in trees for a little while. Okay, all right. Now, language one is just the language of arithmetic expressions. Then eventually we'll build up to the language of Boolean expressions and if statements and while statements. So we're going to build our language. What we're going to do is we're going to build a language up to the equivalent of about a baby C. Okay, we're going to build from just arithmetics And we'll keep adding features to our language until our language is about the same as baby C, meaning it'll have a couple data types like ints and doubles. It'll have functions. Um, it'll have arrays and boolean. You'll have ints, doubles, booleans, arrays, and functions. Okay, and that'll be a baby language that lets you write simple little programs. Okay, so we'll build up. We're gonna language 0 is the language of just trees with no meaning to them. Language 1 is going to be the language of arithmetic expressions. Next week we'll do language 2, which is going to be arithmetic expressions with Boolean expressions mixed in. Then language 3, the next week, will give us variables. It'll let us declare variables. That'll be language, let's see, no, language 2 will be, 1 is arithmetic, 2 is Boolean, 3 is variables, and I think 4 is going to be with if statements. And then the next one will be while loops, and then eventually we'll add functions, which will be the hardest step. The most work will be when we give our language the ability to declare functions. Okay, so that's what we have, and we'll stick to a tree language for everything. Everything's going to be a tree language, and then at some point we'll go and give our language this kind of notation. Okay, we'll switch from tree language to traditional language, but we'll do that later on. After we've built kind of an interesting language, then we'll give that interesting language essentially what you might think of as a real syntax, not this baby syntax. But believe me, this baby syntax, there's plenty of people who like it. Like I say, Clojure is a modern programming, a very popular, powerful modern programming language that uses this tree language. It uses a slightly more sophisticated version of this tree language. It's not just the tree, it's the tree language with a little bit of extra features thrown in. So Clojure isn't really entirely a tree language, but it's pretty close to it. Okay. Okay, so now let's look at the details of language 1. Here is the grammar to language 1. Language 1 is a tree language. So it describes trees, but it's a specific tree language. It's a tree language that describes arithmetic expressions. So another way of call this is the language of expressions, of arithmetic expressions. An arithmetic expression is either an A expression or an integer. Okay, so an expression is either an expression or an integer. An integer is a sequence of digits. The interesting thing is here, what's an arithmetic expression? Arithmetic expression is either left parentheses plus operands or left parentheses minus an operand. So it's either addition, subtraction, multiplication, division, quotient, and exponentiation. So what this is addition, subtraction, multiplication, integer division, remainder, and exponentiation. And the only data type right now is integer. So there's no doubles in this language. It's the language of integer arithmetic. Now, here's something a little bit interesting. The plus operator takes one or more parameters. Okay. Now, let's see. Now, what that means is, let me close this in. Here's what I mean by that. You can write plus 5. That just means the number positive 5. Okay. But you can also write 5, 6. That means the sum of 5 and 6. But you can also write 5, 6, 7. That just means add up 5, 6, and 7. Or you can, it's not just a binary addition. You can add as many numbers as you want up. Okay. So most of these Lisp-like languages, they let the plus operator take as many operands as you want. So it's not like in Java and JavaScript where plus is a binary operator. The plus can be anywhere from 1 or more operands. If there's just one operand, it just says positive number. That's just the same thing. This guy is the same thing. It's just saying 5. So this and this mean the same thing. But this means add them. Now, later on, we'll see that with subtraction, we have similar kind of thing. But this means the number -5. That's the same thing as -5. See, this is the number -5. this is the negation of positive 5. And if you do this, that's the same thing as positive 5, because that's the negation of negative 5. Okay, so subtraction can take 1, or you can do this. Oops. That means 4 minus 5. Okay, this would mean 4 minus 5 minus 6. But then you have to be careful about what order, how you mean that. We're going to mean that as 4 minus 5. Then after you find that result, then you subtract 6 from that. Okay, so we let these operators have different number of operands from 1 or more. Okay, so now the way that's read is this tree, this root has a left branch, and then it has, this symbol means 1 or more right branches. So the star here is read as 1 or more. So you have a left branch and 1 or more right branches. Okay. Oh, and for subtraction, actually, I take it back. I defined the subtraction, so you're not allowed to do this one. I'm sorry. The subtraction only allows 1 or 2 operands. So I, just for the heck of it, I designed subtraction to be a left operand, and the question mark here means 0 or 1. So there's either no second parameter or there is a second parameter. So that means you have either 1 or 2 parameters. So that means subtraction either looks like this or looks like this. 1 operand or 2 operand. This is then this is negation and this is subtraction. Okay, so this is actually the negation operator, and this is the subtraction operator. So they're actually different operators, slightly different operators. That's like on your TI calculator, these are different symbols. If you remember on a TI calculator, there's one key for negation and a separate key for subtraction. Okay. Now, multiplication, if you think about it, there is no meaning to this. So multiplication doesn't make sense with 1 operand, like this makes sense with 1 operand. And this, oops, and this makes sense with 1 operand, positive 5. This makes sense with 1 operand. This doesn't make sense with 1 operand. So over here, the grammar says that multiplication takes a left operand, and this is read as 1 or more branches. So there's 1 left branch and 1 or more extra branches. 0 or more, 0 or 1, 1 or more. These are standard symbols. These are standard symbols in the language of regular expressions. And grammars use these things all the time. Star means 0 or more. Question mark means 0 or 1. Plus means 1 or more. Okay, so that means this one's there for sure. And then since this one's 1 or more, there's definitely 1 more expression, and then there might be more than 1. This one's there for sure. Since this is 0 or 1, this one might be there 0 times, so it's not there, or it could be there exactly 1 time. And since this one's 0 or more, that means that there's this left first child, there may be an extra child, or there may be more than 1 extra child. Then for these other operands, I made all of them exactly binary. There's 2 operands. See, there's none of these extra little markings. So that means division takes exactly 2 operands. Division takes exactly 2 operands, and exponentiation takes exactly 2 operands. And I kind of did this just to show you the different ways of designing these things. So addition takes 1 or more parameters, subtraction takes 1 or 2 parameters, multiplication takes 2 or more parameters, and these take exactly 2 parameters. Okay, just to show you the variety of ways you can define these. Okay, so that's what our language looks like. So expression this like, oh, but notice that this is recursive. So what are you taking the subtraction of? You're taking the subtraction of an expression with another expression. So that means over here, you can take the subtraction with a another expression, and with another expression. Okay, so that's the subtraction of two operands, where this one is recursively another expression, and this one is recursively another expression. Okay? But on the other hand, this could be an expression too. So that could be the division of two numbers. Okay, so this guy is the product of two things, that expression and that expression. So the grammar is recursive. You can take the product of any number of expressions, and then each expression is either a sub-expression or just a number. Okay, so notice that this goes back up to here. This means either another expression or a number. And I didn't have to write it this way. I could have written it as expression is any of these and just put, I could have put integer down here at the bottom. It really doesn't matter. See, I could have written it this way. Kind of 6 of one, half dozen of the other. Yeah. So this says an expression is either a tree or a root by itself. And the root would be, if it's a root by itself, it's an integer. Okay. So, or I could write it the way I had it, where I write it this way, where an expression is a a more complex expression or an integer. A reason for writing it this way is because later on our expressions are going to get more and more complex. So I'm writing it like in two levels here, just to say that I can write this as a two-level grammar instead of writing it as a one-level grammar like this. I mean, this is more compact. Okay. In fact, over here, I could even just put this into here and not even have this thing here. But then it comes a little bit harder to read. Yeah. Then you have to realize, well, what this thing really means is an arbitrary integer. But now the grammar is much more compact. Compact doesn't always mean more readable. Compact can, fewer lines of code can be harder to read than more lines of code. So I like it better like this, or even like that. To me, this is more verbose, but a little bit more explanatory of what's going on. An expression is an arithmetic expression or an integer. Okay, and then an arithmetic expression is got the arithmetic operators in it. Okay, so then eventually expression is going to be either an arithmetic. See, what's going to be eventually? It's going to be like this. An expression is either an arithmetic expression or a Boolean expression or an integer, and then this will grow. So an expression, our language will grow. So this part will grow with our language. An expression can be either an arithmetic expression or a Boolean expression. Later on, it might be including, say, a floating point expression, or we can build the language up a more elaborate language. Okay, so right now, there'll be eventually we'll get multiple kinds of expression as the language grows. So right now it's just an expression is arithmetic or an integer, but arithmetic, an integer is an arithmetic expression, so it's a little bit indirect, but because these two are a little bit redundant. An integer is an arithmetic expression. Okay, all right. Now, I want to write programs in this language. Here's a program in that language. It's an arithmetic expression. This is its abstract syntax tree or its expression tree, but that's a program in that language. And I want to run that program. Okay, so this is a program in the language, and I want to run that program. So I take that. Now this is also this is a tree in our tree language. See, this is two things right now. It's a program in language 1, but it's a tree in language 0. It's this tree in language 0, which is the abstract syntax tree of this program in language 1. Okay, so things are like playing double duty here. that thing is both a program in language 1 and it's a tree in language 0. But as a tree in language 0, it's the abstract syntax tree of our program. So we build that tree. Okay, so we use the parser for language 0. That's the language 0 part. I should have put, this is the language 0 parser. Okay, because this is actually still a piece of language 0. So that's actually the language 0 parser, just straight out of the last programming language. It builds the tree. Okay, then I want to, well, then I can do things like I can pretty print the tree. But what I really want to do is I want to do the walk of this tree, the post-order evaluation. I want to do a post-order evaluation of this tree, which then evaluates this expression. So I want to do the post-order evaluation of this tree, which goes down here, evaluates the left branch, evaluates the right branch, then does that operation. But to evaluate the right branch, you have to go down here, evaluate the left branch, evaluate the right branch, then do that operation. Okay, so that's in a program here called evaluate. This program evaluates, which is another way of saying interprets. We're writing an interpreter. We're writing an interpreter for a very basic language, a language of just arithmetic expressions. It interprets the abstract syntax tree. So the evaluator doesn't take in the language. The evaluator takes in the trees from the language. So first you have to take the thing in the language and build the tree out of it. Then you can pass the tree to the, down here is the eval the tree. Okay, so after I pretty print the tree, so here, yeah, I build the tree, print it out a couple different ways, but the real thing I want to do is eval the tree, evaluate it. Okay, and what does the evaluator look like? Okay, let's just follow through. It's going to be a post-order traversal of the tree. Okay, so what does that look like? You give this guy a tree, okay, and then he says, well, I look at the root of the tree. The root of the tree is the operator. It's either a plus, a minus, a multiplication, a division, a remainder, or an exponentiation. If it's one of those, I call this other function that evaluates it. Okay. Now, the tree, if the root is one of these guys, then it's going to have subtrees, and I want to evaluate them recursively. If it's not one of these, remember the tree language was you are either, or was it? You're either an expression or an integer. So right now my evaluator check first for, so my evaluator first checks are you an expression? If you're not an expression, you should be of degree 0. Because if you're a number by itself, you should have no children. So it checks if it's degree 0. If it's not degree 0, something's wrong. See, this is the error checking. If you give me something that's not one of these operators and it's not a degree 0, something's wrong. Okay. Now, if it is degree 0, I still have to check, does it match the regular expression for an integer? If it does match the regular expression for an integer, I parse int using the Java parse int, and that's my result. If it doesn't match, and this is more error checking, if it doesn't match that, throw an exception. See, I throw exceptions when things aren't right. So my evaluator is looking for mistakes. So that there's extra code in here for making sure that there's no mistakes. So check if the tree is one of these branches. If it is, recursively call this thing that evaluates the arithmetic expression. So if it's an arithmetic expression, evaluate arithmetic expression. Else, it should be an integer. So check if it's an integer. If it is, parse it. If it's not an arithmetic expression and it's not degree 0, like maybe it's got, like somebody did something like they did a tree with an improper operand. Like what if somebody gave me a tree to parse? Somebody could do this. Well, I don't have an AND operator yet, so that should just give me some kind of error message. So my evaluator would say, okay, the root is AND. That's not this, or that. So it falls into here. Oh, it's not degree 0 because it's got operands. But if it's not one of these operators and it has operands, there's something wrong. Okay. So this thing will throw an error until we add that operator into the language. Now, when we eventually add that operator to the language, then that'll show up in this list of operands. But right now, this will cause an error. Okay. Another example would be if I did something like this. If I just gave it X. Okay. X is not one of these. X is degree 0 because it's just a root by itself, but X doesn't match that regular expression, so it's going to throw an exception. Okay, so if I ask my evaluator to evaluate that, it's going to blow up. Now, if I ask it to evaluate this, it'll be okay, because 5 is not one of these, but 5 is degree 0. 5 matches that pattern, so now I'll parse 5 into 5. Or, for example, I'll parse 534. 534 is not one of those. It is degree 0. It matches that pattern, so I'll parse the string 534 into the number 534, and that'll be my result. So this thing would evaluate. On the other hand, this won't evaluate, but because of recursion. That's a tree that has 4 or 5. Okay, it matches that node. So it would then call evaluate expression. Evaluate expression gets this tree. Okay, it gets the root node. So that gets this plus. So now this guy represents the operator. Okay, it evals recursively the left branch. So it evaluates recursively the left branch. Now, when you evaluate the left branch, you go all the way back up to eval. You're way back up here now. But now that left branch will be this case. The left branch will give me 45. Okay. Then after evaluating the left branch returns, I'm ready to start evaluating any right branches. If there is a right branch, eval it. So now I'm evaluating this guy, but it's going to blow up. Because now when I evaluate the right branch, the first subtree, I'll get back up here. It won't be one of these. It'll be degree 0. It won't match this. So it'll give me an invalid expression. So this guy won't evaluate after a couple of recursions. It'll blow up on, oh, you can't give me a variable. The language doesn't have variables yet. Okay, so that's a legitimate arithmetic expression, but this subtree here is not a legitimate expression because X is not an expression yet. Okay, okay. So this thing is this is a recursive evaluation. It's a post-order traversal of the tree. Okay, and it's not a lot of code. You know, you can see that it's a little over 100 lines of code. A lot of the code is error checking. You know, we're not assuming that we're past a perfect tree. So since we're not assuming that we're past a perfect tree, since someone could give us ill-formed trees, our program shouldn't blow up and crash on an ill-formed tree. So it's got to do error checking. Okay, but the key idea is that you eval a tree by essentially what you're doing is grab the root, get the left branch, get the right branch. You have to check if it's, now here's where you have to figure out, are you doing addition, subtraction, multiplication, division, quotient or exponentiation. See, at some point, you have to figure out, well, exactly which one of these guys am I doing? The grammar says I have all these operators. So at some point, the code actually asks, am I doing this, 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 or that? And over here, that's where after you've grabbed the left branch and evaluated it, and after you've grabbed the right branch and evaluated it, then you could start, then you ask, well, is the root this guy? Is the root this guy? Now remember, if the root is this guy, there could be more sub-branches. So if the root is this guy, we've gotten 2 branches, but then here's a for loop that says, well, there might be more branches because we might have a tree that looks like this. So we get the first branch, we get the second branch, we get the first branch, get the second branch. I'm sorry, this is getting the first branch, see subtree 0. This is getting the second branch, subtree 1. Now we can start doing the addition, but then we have to ask, are there more branches? Because if there's more branches, we have to keep going and adding on. Well, after we've added 45 to 5, then we have to add on the 6, add on the 7, add on the 8. So we have to keep iterating until we get to the end of the tree. We have to ask how many branches are there. Here's the root, and we have to iterate through all its branches to make sure we pick up all the operands. Okay, so that's the post order traverse. That's the traversing the tree. We traverse the first branch, second branch, add those 2 results together, then drop into the for loop that says if there are more branches, evaluate each additional branch. Okay, so after we go through all the additional branches, so grab the first branch, grab the second branch, then iterate through the remaining branches. Now, subtraction doesn't need to do that because we said our grammar said the subtraction only has 1 or 2 branches. So there's no for loop under subtraction. But multiplication has a for loop because multiplication can have arbitrary number of branches. So the plus and the multiplier are the ones that have an arbitrary number of branches. So they have to iterate through possible sub-branches. These guys only have 2 branches. See, this one only has 2 branches. This one only has 2 branches. Well, yeah, 2 branches, left and right. Okay, so remember the grammar was plus and multiply could have arbitrary number of branches. All the others have, well, this one has 1 or 2 branches, and these have exactly 2 branches. So the evaluator has to account for all that. Okay, so the evaluator, it says, well, when I'm in here, I have to iterate on branches. When I'm on this root, I have to iterate through branches. But if I'm at this root, I only have 1 or 2 branches. If I'm on this root, I have exactly 2 branches. Okay, so the logic's a little bit messy, but it's more or less a straightforward post-order traversal of a tree. You're walking the tree. This guy just is a plus with a bunch of branches. Okay, it's a plus with a bunch of branches, and you have to walk across those branches. You have to walk across the branches. You think of it, very dynamically. It's a tree, and there's the 45 branch. Then there's the 5 branch, and then the 6 branch, and then the 7 branch, and then the 8 branch, and you just walk the tree. You grab that branch first and that branch next, because there's going to be at least 2 branches. Then you just keep walking across this tree, pick up the 6, add it to that result, pick up the 7, add it to that result, pick up the 8. Then when you get to the end, the for loop ends. Okay, so you iterate through the branches. Okay, All right. It's kind of interesting. Okay. Let's play with this language. Now, notice that there's a lot of files in here. You have to get used to reading kind of semi-large pieces of code because I've taken everything and put them into little pieces. So for example, this parses a tree expression, and then there's possible parse exceptions. Okay. After I parse the tree, this one allows me to pretty print it. Oh, before I can parse the tree, I have to tokenize it, which is to lump it into its tokens. So I need a token class, a tokenizer program with possible tokenizer exceptions. Okay. I need something that defines the tree data structure. This thing lets me print out the trees in pictures. So that converts trees to dot, which lets me create pictures of them. Okay. Here's the evaluate program that walks the tree, and it could throw evaluate exceptions. Okay. And then one thing I did is I took all that code and I bundled it into a jar file. So all those pieces that are parts of what define the language, I put them into a jar file, and then I wrote a program that lets you, it's an interpreter for this language. See this thing here? This is an interpreter for the language. Okay. What this thing does is it's a read, eval, print loop. It lets you, well, let me just run it and show you. This thing has been compiled into this jar. This one also got compiled into the jar file, and this one runs the jar file. Here's my read, eval, print loop for my arithmetic language. What's 3 times 4? 12. What's the sum of 3, 4, and 5? The sum of 3, 4, and 5 is also 12. What is the sum of the product of 3 and 4 with 5? Okay, so that's 3 times 4 is 12. 12 plus 5 is 17. So I've got a REPL, a read, eval, print loop for my language of arithmetic expressions. Okay, all right. I can goof up. I got too many parentheses. I could goof up a different way. I forgot to close the parentheses. I could goof up a different way. That's not a valid expression. Okay. I could goof up another way. Notice this time I got a tokenizer error. My language doesn't even recognize at as a it recognizes the at sign, the ampersand sign, because eventually we want Boolean expressions. So it recognizes ampersand as a valid token, but it doesn't evaluate it yet. It doesn't even recognize the at as a valid token. So you get a tokenizer exception if you use the at symbol, because right now the language doesn't even envision having an at operator. So I didn't even put that into the tokenizer. Another example of goofing up is, now notice that X is an invalid, no, notice plus is nothing wrong with it. Plus of something and something. But when it recursed into the X, it said, but X is not a valid expression. The language doesn't know how to evaluate X yet. Now notice here, the multiplication of two things is okay. The addition of two things is okay, but Y is not a valid expression. So what happens is it evaluated this thing as far as it could, but when it got to the Y, then it threw an eval exception because it didn't like the Y, because Y is not a valid expression. When we give the language variables, then Y will become a valid expression. Okay. If you write, it doesn't understand infix notation. Okay. So it just gives you a weird parse error because this language doesn't do infix notation. It only does prefix notation. Okay, and That's not an operator. Oh, that crashed my program. There's probably a little bug. Let me try that again. That's kind of weird. I did. Oh, I have to figure out what's wrong with that. Yeah. So notice I've got some little bug in the program. It's blowing up on. Oh, let's see. That was, I think it was 2 stars. Yeah, I have to go through and figure out why that blows up. What if it blows up on other things like that? Let's try. Yeah, see that's just, there's no operator plus plus yet. There will be a plus plus will be an increment operator later on. That's going to be the AND operator. I don't know why that too. I have to go. I'm curious. I have no idea what could be wrong. Why star star? Oh, let me try 3 stars. Huh? I wonder what star. I have to go through and figure out what's wrong with the stars. Why they're causing the program to blow up. Okay. So what we're building is a little language system. You know, we've got an interpreter for our language. You know, this interpreter is using all these other files. Oh, and every time you interpret something, it builds a little tree for you here. Yeah, it builds a little tree here. Okay. Oh, let me try something. One last thing. Clean up. Now let's see if I get a picture of what's wrong here. So, oh, there. Okay, now there's a tree. Oh, it tokenized in a really weird way. And that probably, see, the 2 stars tokenized as a star star. So it tokenized in a really weird way. It didn't tokenize as a star star token. It's tokenized as a star with a star as an operand. Okay. Oh, I wonder if that thing parsed, I wonder if it tried to parse that guy as an int and then the parse int threw an exception. I wonder if that tried to parse this guy as an int. Okay. I probably should just add, well, yeah, right now this is a baby language. It's not trying to be a complete programming language. So there's going to be little glitches in it because trying to get rid of the little glitches can be pretty hard. So I'll see if I can fix that one. But what it's doing, see, is I can tell now that it tokenized it as a single star, and then the other star ended up being an operand. So this star ended up being an operand to that star, and then that somehow, I bet what happened is it tried to parse this guy as an int, and that's probably what blew it up. That's my guess. But we're building a little language system, and all these files together make up the language system. So inside this jar file is the evaluate program, the eval exception, the parse exception, the parse tree program, the tree class, the tokenizer classes. All those things are bundled into the jar file. Then if you double click this thing, you run the jar file, which is the interpreter. And we'll keep building this interpreter up into make it more and more powerful language as we go along. Okay. Your homework is to read this code. There really isn't right now a textbook that your next programming assignment is going to be to add to this interpreter. You're going to eventually you're going to be adding features to this interpreter. So your goal is to read this code and figure out how it works. And then, assignment 1 is due on Monday. Then your assignment 2 is going to be to add something to this interpreter. I'll show you, you'll see what it is. But you're going to grow, we're going to grow the language in class, and you're also going to grow the language in a slightly different way in the homework assignments. So we'll grow the language one way as we develop it in class, and you'll grow the language a different way. In each homework assignment, you'll be growing the language in some small way, while we grow the language in other ways in class. Okay? All right, so we run out of time. And if you have questions about any of this code or the first homework assignment, send me an email. Let me know if you have any questions at all. Otherwise, anybody got any question before we quit? Any question right now about what we talked about today? Any question at all? Okay. So then I'll go ahead and I'll stop the class, and we'll meet again on Monday. And on Monday we'll start with another language. We're gonna go. We'll add Boolean expressions to this language. On Monday we'll do the language with arithmetic and Boolean expressions, and that'll let us dig a little deeper into both arithmetic expressions and Boolean expressions. So on Monday we'll grow the language a little bit more. Okay. See you on Monday. Bye bye.